Einstein that brings out these postulates, and we call him a genius. And of course he is. And therefore his thoughts are not going to be usual thoughts, not things that we are used to. For example, we are used to relative velocity in the sense that if you have two objects moving in the same direction, one moving at 10 meters per second, the other moving at 4 meters per second, the relative velocity of one with respect to the other is 6 meters per second, right? We are used to that. And if they're moving in opposite directions, it's 14 meters per second. So we're always used to this. This is called Newtonian mechanics. But suddenly Einstein comes and says, okay, that's fine, that's good. But you cannot apply this to light. Because he says the velocity of light or the speed of light is an absolute constant. It does not depend on the source or the observer. That's the first postulate of what is called the special theory of relativity. Again, there are two parts of relativity. One is called the special theory, the other is called the general theory. And we are only studying the special theory. Are you with me on that? And it's built on two postulates. The first postulate is what I told you just now. The speed of light is an absolute constant. It does not depend on the speed of the source or the observer. So if light is coming towards you and you are moving on a rocket, is the speed of light going to be affected? No, it's always going to be 3 times 10 to the power 8 meters per second. You can be going towards the photon. You know, photon is the light particle, right? You can be going towards the light particle, going away from the light particle. It doesn't matter. The speed of light is a constant. The second postulate is built on what's called the inertial frame of reference. Have you heard of inertia? Inertia, what's the idea that you have of inertia? Yeah, the tendency of an object that moves to keep on moving. That's called inertia, right? But before we get into all that, you have to know rest and motion are relative. So you always have to have a frame of reference. That's a word that you're going to hear a million times. What do you mean by a frame of reference? When I'm moving here, what's the frame of reference? It's the lab. It's the classroom, I mean. Isn't it? Because if you compare me with the sun, if my motion is studied with respect to the moon or the sun, it's going to be totally different, isn't it? Because isn't the whole earth rotating? So the frame of reference is very important when you study motion. The frame of reference is what you compare the motion with. You always imagine that there is an X, Y, Z axis fixed in the room, which is easy for you to do. If you look at the corner, you can see the X, Y, and the Z axis, right? So that's the frame of reference. Keep that in your mind. And an inertial frame of reference is an unaccelerated frame. Any frame of reference that is moving with a constant velocity is called an inertial frame of reference. And according to the first postulate, any law of physics holds good in all inertial frames. Let me explain that. All laws of physics are equally good if it's an inertial frame. Let's assume that there is a ship in the ocean, and it's a calm ocean, no waves, nothing, and the ship is moving in a straight line with a constant speed. Can I say that its velocity is constant? Because velocity is a vector, right? So if it's moving in the same direction with the same speed, its velocity is constant. And let's try to do an experiment that we did in the lab. For example, the projectile lab, the ballistics lab. Do you remember that? Where you shoot out something. Let's try to do the same experiment on the deck of that ship. Will you get the same results as you did in the physics lab based on this postulate? So this is where I'm checking your understanding. Now, the ship is moving, but I told you how it's moving. It's moving at a constant velocity. Is it an inertial frame of reference? Yes, it is. Because it's unaccelerated, It's moving at a constant velocity, right, in the same direction. So whatever results you got when you did it in the physics lab, you will again get the same if you do it on that frame of reference. Have you understood what I said? So that's the first postulate. The laws of physics are valid in all inertial frames of reference. Second one, the speed of light is an absolute constant. It does not depend on the speed of the source or the observer. I did talk about this for such a long time. I told you it's an unaccelerated frame of reference. That means it should move with constant velocity. And the Earth is considered to be an inertial frame of reference. Approximately. Keep that in mind. The Earth is considered to be an inertial frame of reference. Although it's rotating and all that, we take it as an inertial frame of reference. All right. Time dilation is the next topic. Time is relative. In the general theory of relativity, actually, we can prove that we were born before our dads were born. But we don't have to go into that. But at least understand where I'm coming from. Time is relative. So it depends on where you're looking at time from. Now, up until this time, we can't even think about this. So now, what do you call simultaneous? Loses its meaning now. If I drop two objects together, wouldn't you say it's simultaneous? Right? No, it depends on where you're looking at it from. So for one person, when I drop two objects, he will say, yeah, he dropped it exactly at the same time. And let's say somebody's just zooming by on a rocket, imagine, right? And he's watching the same thing from his frame of reference. According to him, he'll say, no, he didn't drop them at the same time. So now time is also relative. Now this diagram shows you that elapsed time for a foot race is the same for all observers. That's what we are used to, small timings, Yeah. Otherwise there would be a fight, isn't it, if time was relative in a race? Imagine everybody could come up and say, I won the race actually, from this frame of reference. That never happens. Relativity is practical only when you come to high speeds. I'm going to prove that. There's only two derivations that I'm doing in this chapter. No, three, sorry. Three, the first one is the most important. And we're going to get the idea of time dilation. I do not know whether you can make out what's happening. I'll take 1 minute to that. Try to look at the diagram carefully. There's a train moving. A passenger is seated there. Can you see that person? Yeah? Can barely make out. There are two light bulbs at the two ends, and the person is right in the middle there. And the two light bulbs produce light. It's like a pulse, just a pulse, together. And this is being watched by an observer. So that's observer A in the train, B outside, watching the same thing. And it's very clear to anybody that to this guy who is outside, the two bulbs will seem to be producing simultaneous pulses, isn't it? To the guy who watches it from outside, yeah, he'll say, yes, both the light bulbs produce light at the same time. But if you ask the passenger, you can see that the light from here, because this train is moving in that direction, to the right. So don't you think that the light from this light bulb would reach the passenger a little bit earlier than light from here would? Come on, does that make sense? So if you ask the passenger or the observer, hey, is that simultaneous? Person would say, no. Did you get it? A simple idea. But if the train was moving in the opposite direction, then the light from the other light bulb would have reached the passenger first. Either case, according to that person, it's not simultaneous. Okay, there is a thought experiment. This whole chapter is based on thought experiments. So you'll have to do thinking. It's a rocket. There you go, thinking. And there is a clock, and this entire chapter depends on that, really. There's a clock on the rocket, that's the astronaut, and there is a light source here that gets reflected from a mirror and comes back to a receiver. So the whole experiment is taking place in the rocket. Are you with me? And there is a person observing all this from the ground. So the observer is on the earth. What's going to happen is, if you take this distance as d, caps D, what time will this person measure, the astronaut measure, for the light pulse to go and come back? If c is the speed of light. C is always representative of the speed of light, right? So what's the time taken? According to the astronaut, how much time does it take for the light pulse to go from the source and get reflected and reach the receiver? Go ahead. How much time? Time is distance divided by speed. What's the distance traveled? 2d. And the speed of light is? Okay, so it'll be 2d by c. Everybody got that? Now, which is the moving frame of reference? This is always a point of confusion for students. Which is the moving frame of reference? Is this guy moving with respect to that clock? Is that guy moving with respect to the clock in the rocket? No. See, that's where the confusion comes in. Actually, the rocket is moving. But because the clock is on the rocket, or in the rocket, whatever, it's not moving. So he's going to, whatever time he's going to measure, we're going to call that delta T naught. The zero represents it's a frame of reference at rest. What about this guy? What time will he measure? According to him, is that clock going to be moving? Yes, that clock is going to be moving. That's what I mean. According to him, But if he has a clock right by his side, that clock is not going to move. Be with me. You see the point of confusion is coming up. But I'm talking about that clock. Ready? That's moving with respect to him. Wouldn't he measure a different time? Why? I'm going to show you this. Let's say this distance is s. Watch. By the time light goes from the source to the reflector, the mirror has moved, isn't it? Hasn't it moved from this point to this point? And by the time light returns to the receiver, hasn't it moved an equal distance away again? Yes. So when you consider this distance move, wouldn't you have to take this distance? According to this guy, isn't the distance moved this one? And what is that distance? That distance is going to be, help me out, if you call this L, then that distance is square root d squared plus L squared. Everybody knows that, isn't it? Okay, let me write that down, and so you'll understand. What's the meaning of dilation? Is it, does it mean make small or make big? Okay. Time appears to be dilated. Time always appears to get bigger, is what I'm trying to say. I brought that diagram again, and I said the reference frame of the spaceship, delta T naught, is 2d by c. All right, but for the reference frame of the Earth, and now I'm going, speed is distance by time, isn't it? Speed is distance by time. The distance is 2 times square root d squared plus L squared by delta t. Now it's delta t. Did you notice the difference? Delta t. Okay, speed, and you know how we got 2 times, because it's once, twice, okay? 2 times that distance divided by t. Now it's only math, simple substitutions. And if you are watching carefully, you know that 2 times the length, 2 times the length is the velocity of the rocket multiplied by the time. You know, when you try to write all this, don't miss the points. Hasn't it moved from here till here, correct? In delta t seconds? And don't you have to consider the speed of the rocket now? Therefore, distance is speed multiplied by time, which gives, this is 1 by 2. I'm going to substitute there. I'm going to substitute for this length there on the next slide. That's what I'm going to do. So everybody's clear on that. Let's substitute for that and rearrange and get a magnificent form. Okay, I've written that again. Make sense? We can't afford to take too much time on such things. That's simple substitution. And if I square both sides, what's going to happen? Okay. Because the 2 becomes 4 and the square root vanishes and I'm distributing it, so it's 4d squared by delta t squared. That's the first term. And the second term plus, because the other terms will get cancelled. Correct? 4 outside gets cancelled with this, and delta t squared gets cancelled with this when you square it. Okay. Rearrange that. Okay. Simple. Make delta t squared the subject. And we are almost there. Divide throughout by c squared now. On the right side, in the numerator and the denominator, I have divided by, and I've taken the square root 2. I've done 2 things. I've divided each term. Can you see what I did? If you take the square root of this, that's 2d, and I've divided each term by c squared, or when I take the root by c. Okay, so can anybody see what this is? What's 2d by c? What was 2d by c? Delta t naught, isn't it? So now I can substitute. I'm trying to show how I got that. I took out c squared, you know. I can substitute that. It's this. Because 2d by c, as I've highlighted, is delta t naught. And that's a very important equation that you got. And let's talk about this term for some time. What's this? What's the v here? What's that? That's the velocity of the frame of reference, isn't it? What is its lowest value? 0. If that becomes 0, then you know delta t is equal to delta t naught. Yeah. Correct? Yes. And what's the highest value? According to Einstein, no object can have a velocity greater than the velocity of light. Now, why does he say that? Let's say this velocity is equal to c. What happens? If v is equal to c, then the denominator becomes 0, and then this becomes undefined. So that's why Einstein says the maximum speed is the speed of light. Nothing can move faster than the speed of light. I think you understood. But if that happens, as the velocity approaches c, let's say the velocity of something is 90% of the speed of light. Do we have stuff like that moving so fast? I mean, if we don't, then why should you even consider objects moving at 90% the speed of light? Because we do. What did you think are the speed of electrons in an atom? You knew that the atoms are small. You know that electrons move in particular orbits, isn't it? Did you know that their speeds approach the speed of light? Let's take the smallest atom. Which one? The simplest atom, the smallest, hydrogen. The electron in the first orbit, you know, it only has, how many electrons does hydrogen have? I was showing 2. 1. And that electron is rotating in the first orbit with 1/10 of the speed of light. Did you hear me? So we do have particles that move fast. And when that happens, don't you think that there will be a big difference between these 2 times? Come on. Will they be equal? Not anymore. So when you start talking about molecules and atoms and you start talking about fast-moving particles, there is no way you can use Newton's formulas there. It will not work. You have to consider relativity. But do we have to consider relativity when we talk about a bus moving on the road? Because the velocity of that is negligible compared to the speed of light. So that's why all this time and all these chapters, we did not have to talk about this. Now, so this is the gateway into study of stuff that's moving fast. So before that, you had to know this. That's why the chapter is important. But anyway, for those who are just interested in the math, that should... Oh, what did I do? Okay. For those people, I'm going to define something so we don't have to write it again and again. Yeah, that's the reason that I got. But I'm going to define something. Watch. This is the formula that we got. And let's take gamma. Let's define gamma as square root 1 by square root 1 minus v squared by c squared. Because that term is going to keep repeating throughout this chapter. So let's call it gamma. All right. Can somebody tell me what will be the smallest value of gamma? Based on what I told you up to this point? 1? Yes. And what will be the highest value of gamma? So can I say that gamma is always going to be greater than or equal to 1? If you keep that in your mind, probably you may not go wrong when you work out problems. Because gamma can never be less than 1. Okay. So that's what I've written there. Therefore, can we write delta t as gamma delta t naught? Yes. And since I told you that gamma is always greater than 1, isn't it true that delta t is always greater than or equal to delta t naught? Come on now. Yeah, because I told you that gamma is always greater than or equal to 1. So this time has to be greater than or equal to this. That's why it's called what? Time dilation. What am I doing? Of the postulates that Einstein made. Length is going to contract. Momentum is going to be different. Kinetic energy, not 1/2. What's the formula for kinetic energy? 1/2 mass times velocity squared. No more. Let's look at them one by one. But before that, an example, a cool example of, have you ever heard of a particle called muon? If you've not, it's a particle that's born and dies within milliseconds. So a muon's lifetime is like 3 times 10 to the negative 3 seconds. So let's assume that inbuilt in the muon, you have a clock. Are you with me? So it's able to measure its own lifetime. And then you measure it from outside the muon, of course. Are we both going to get the same time? No. And if you look at this clock, and you see that surely this clock is going to measure a smaller amount, this is going to be bigger. That's what we call time dilation. And all these materials are taken from OpenStax because this is going up on YouTube. This is financed by Bill Gates Foundation. They're trying to bring out textbooks free for all subjects. And we've started using college physics text from before the last 3 semesters, we started using that. Free textbooks for everybody. You may want to Google OpenStax. They brought out biology, chemistry, physics, math, brilliant textbooks. They're trying to destroy the textbook publishing companies who we know charge a lot of money, don't we? It's absolutely free for all students, for all teachers. Don't you like that? And you can use their materials, no copyright issues. No copyright. Do you see any copyright? I did not have to erase anything, so it's brilliant. Somebody's thinking. Okay. This example is a good one. It's called the twin paradox. We are still talking about time dilation, okay? Still talking about it. Let's say that there are twins. Why should I say 2 twins? Okay, there are twins. One undertakes a space journey on a rocket, of course, and comes back after a certain number of years. And you know what's going to happen when he comes back, or he or she comes back? We'll find that the other twin has grown really old. The one that's returning is going to be young. Look at the time. This person will measure, let's say 10 years have passed, but on the Earth, 25 years may have passed. Now I'm thinking, man, I want to be the one who undertakes that space journey just to catch that twin and say, hey, you're old. And again, on the other side, you're looking at this and saying, practically, is this going to make sense? Is this going to happen if you undertake a long journey for 10 years? So what's wrong? Is Einstein's postulate wrong? Is his idea wrong? You know the meaning of the word paradox? What does that mean? That can't be explained, right? But this really can be explained. Actually, paradox means, if you look at it from the other side, if you look at it from the point of view of the twin who stayed back on the Earth, you could also say that the other person is going to grow old, if you are with me. Watch. When this twin is going off in the rocket, isn't it correct to say that this twin is moving backwards at the same speed? Hello? So with respect to this twin on the rocket, isn't this twin moving backwards? Can't you understand? So who's moving? According to the guy on the rocket. Okay, according to this person on the Earth, that's easier for us to imagine. Who's moving? Oh, so now it works both ways. So who's going to be older? That's why it's called the paradox. But why do we just waste time on this? Because this is not an inertial frame at all. Is it an inertial frame? Somebody tell me why it's not an inertial frame. Well, one thing, when the rocket takes off, it's accelerating. Second thing, the most important, the twin is coming back, isn't it? Well, change direction, 180 degrees. It's no longer an inertial frame. How many understood what I said? So why do you try to apply ideas like this into where you cannot apply them? So the postulates are still correct. But since these are not inertial frames, that's why we have all kinds of confusion, is the conclusion. Contraction. The second consequence is length contraction. And I'm giving you the formula directly. The diagrams make it very clear. Watch this. The muon just measures the distance it travels in a certain time as 0.627 kilometers, right? But the observer on the Earth measures the same distance as what? 2.01 kilometers. So what happened to the length? As an object moves, what happens to its length? Does it become bigger or does it become smaller? If you look at this formula, you will see you're not multiplying with gamma now. What are you doing? You're dividing with gamma. And you know that gamma is always greater than or equal to. Therefore, L is going to be less than L naught. So that's why it's called length contraction. But remember that this contraction takes place only in a direction parallel to its motion. So if an object is, if you have a meter stick moving parallel to itself, the length contracts only on its length, not on its width. Did you get that? Now that's a good concept question for me to ask, but I can't ask that anymore. Because I said it. The length contraction happens only in a direction parallel to its motion. That's all I want you to know about length contraction. That's number 2. Do you see 2 frames of reference? I'm going to explain those. You don't see the z-axis because I cannot draw it, and you know why. But you see the x and the y. This is the x prime, the y prime. So this frame is called the s prime frame. This frame of reference is called the s frame. And the axes are x and y. Agreed? And initially, to make matters simple, let's imagine that their origins coincide at t is equal to 0. Oh, that's simple enough to understand. So okay, I can only hold it easier this way. So one is moving, The other is not. You can see that. But right when this moving one comes here and it coincides, you stop the clock. So t is equal to 0, and this keeps moving. Got that? Okay. Now, which one is moving according to this diagram? You'll only be able to do problems if you understand this. It is not. I love problems in relativity. You cannot do it by cramming an equation, substituting. No way. Which frame of reference is moving? S prime is moving with a velocity v. Okay? And an event has taken place here. Something happened there. Maybe a small bomb went off. Now, that's not a good example, but still, a small bomb went off at P. Isn't the x coordinate from this origin x? But wouldn't the x coordinate from this moving frame be x prime? And what's the relation between the two? These are called Galilean transformation equations, means Newton's era. What's the transformation between, half of it has already come up, at least you could have read that. Which is bigger? X is bigger, so x should be x prime plus the product of velocity and time, isn't it? That's simple? Yeah. What about the transformation along the y-axis? It won't change because we assume that it's moving parallel to its x-axis. So no change along the y-axis. Any change along the z? Come on. No. If you're with me, no change. Any change in time? According to Galilean transformations, time is not relative. There, the old one. This is the old one. Time is not relative. So he'll say, oh yeah, both the times measured should be the same. The old one. But not anymore. When you consider all that I've been telling you, the transformation equations will change. And before that, what about the velocity? When I say velocity, again, please pay attention. Let's consider that something is moving. Maybe it's a bee flying, okay? Doesn't it have another velocity? So let's call that ux and ux prime. Are you with me? What's ux? What's ux? Don't stare at me. It's of no use. Instead of considering that a bomb went off, I'm trying to say, imagine there is something moving. So doesn't it have its own velocity? Okay. Can't you measure its velocity compared to both the frames? So the velocity of this, whatever is moving, compared to the S prime frame is ux prime. And compared to the S frame would be ux. And this would be the Galilean transformation for that. We know that. Don't we know this? That ux is going to be ux prime plus v. Come on. But when you come to relativity, all the transformation equations change. It's now the gamma thing is going to come. Well, no change in the y and the z, but the greatest change is in the time. These are called the Lorentz transformation equations. So you have both the Galilean and the Lorentz transformation equations. Is this gamma the one that we had defined before? Yes. So those are the transformation. I don't know why I tell stories. Okay. Relativistic addition of velocities. I'm going to derive this. Because it's math, you get a better chance of understanding. So I'm bringing in the math once in a while. Okay. Does everybody know that velocity is defined as the differential of displacement with time? Okay. So ux is dx by dt. Let's make use of the calculus a little bit. And did we not already find that x can be written as gamma x prime plus vt prime according to Lorentz transformation? Yes, we did that, didn't we? Okay. And so how would you differentiate this now? that technically cannot be differentiated. Somebody tell me why. How can? Because you're trying to differentiate with respect to time, and what do you have here? T prime, correct? So unless you make a change that I'm going to show you, see, that's what I circled, I'm going to say, let's take d by dt prime, which is possible now, because d by dt prime of that is okay. But I have to compensate because it was not like that. So I multiply with the reciprocal of that. So you know that technically these two cancel out and I still have d by dt. Okay, so now I can differentiate, and when I differentiate, you get dx prime by dt prime for the first term. Gamma is a constant, of course, taken out. This is dx prime by dt prime plus, what's going to happen in this term? Somebody. What is d by dt prime of this? Velocity is a constant, isn't it? Yeah, so it's just going to be that, yes. And then, of course, I have to write that. Simple. And if you rearrange, what you get is dx by dt prime. Now, that's just defining. Ux prime is dx prime by dt prime, and ux is dx by dt, which we have written already. Okay. Time is given by that. That's the transformation equation. So if you take dt prime by dt, which is 1 by dt prime, it's going to give you 1 plus gamma Vux prime by c squared. Because you're going to get dx prime by dt there. For this term, dx prime by dt prime, that is what? It's ux prime. If you try to understand, you could. Yeah, that's what I'm showing there. Therefore, ux is gamma ux prime plus v by this whole thing. Of course, the gammas can be cancelled out, and you get a very important relation, which I'm writing again, just to show you that it's really important. That is how you add velocities. So, in the original Galilean transformation, how would you add velocities? How would this be? Somebody? How would this be? Ux would just be? Oh, nobody's with me. Compare this with the Galilean transformation. How would it be?
Ux prime plus v2.
That's all. Ux is ux prime plus velocity. Isn't that what we wrote some slides back? Watch. Do you see this? Come on now. But do you see what it became now? That's a very important one, and you're going to have at least one question to do on that for practice at least. The last part. The last part of this chapter, relativistic momentum. No derivation there. Normally, how do we define momentum? Mass times what? Velocity. Can you guess how momentum is going to be defined in this case? Can you guess how? I mean, normally it's mass times velocity. I thought you would guess. It's just gamma times mv. Relativistic momentum is gamma times the classical momentum. You just have to multiply with gamma. That's easy enough. We've already gone through this and all this stuff. Just remember that. Relativistic momentum is gamma times mass times velocity. Can you remember that? And once again, before I leave this, be sure that if the velocity is negligible compared to the speed of light, gamma is going to be 1. So it goes back to our classical definition of momentum, isn't it? Just remember that. So you need not do this when the objects are moving really slowly. That will look like, you remember my example? You spit into the ocean and announce that the volume has increased. It'll look like that when the speeds are so small. All right, so that brings us to the last one. Relativistic energy. Ready. This is, your textbook actually shows you how to derive E is equal to mc squared. Do you want me to do that? It'll take 3 pages and about 1 hour. And then I'll ask you that on the exam to derive it. But it's given in your textbook. But I want to catch it part way so you don't miss the interesting part of it. You know, that's what I'm trying to do. So at least you get the idea of how Einstein gets E is equal to mc squared. I didn't want you to miss that. So that's what is going on here. Okay, that's what we're trying to derive, and this is no more correct. What's K? K represents kinetic energy. At high speeds, at relativistic speeds, half mass times velocity squared. Wrong. Scratch it out. That's not correct anymore. Okay. Now, kinetic energy is this. What on earth is that? Okay, let's look at that. It looks like kinetic energy is the difference between 2 terms, isn't it? All right, this term here is called the rest energy. Huh? So an object is at rest. Does it have any energy? We're not talking about potential energy in this case. Let's say, to make you think correctly, let's say it's on the ground. Because for you on the ground, potential energy is 0, right? Let's assume it's on the ground, not moving at all. Does it have any kind of energy? Yes. And the molecules inside are not moving either. Okay, sometimes you might catch on that. Nothing is moving. Just imagine, it's at absolute 0. You remember, at absolute 0, all molecular motion stops. So it's at absolute 0 on the ground, no kind of energy, but yet Einstein says, yes, it has some kind of energy. You ask him, what do you mean? He says, look, isn't there mass inside it? If you convert all that mass into energy, you would get energy. And people shouted at him and said, don't you know that mass can neither be created nor destroyed? We have applied that so many times in physics and in chemistry. The mass of the products is equal to the mass of the reactants. Haven't you done that? Well, Einstein says, well, you could destroy mass. And everybody's like, what? And then they again shouted at him, but also don't you know that energy can neither be created nor destroyed, Einstein? Now, this man with one statement breaks 2 conservation laws. He says, if you can create or destroy mass, you can create energy. Wow. And nobody seems to agree with him, and he calls it rest energy. So this book here, if you could convert this, all that mass into energy, you get a lot of energy. And nobody believed him. But wait until we get to those steps. And kinetic energy is the difference between this and the rest energy. Do you recognize the gamma in here? So actually, isn't this gamma mc squared? Come on now. Okay, so it's gamma mc squared minus mc squared. Okay, let's try to write it that way. Gamma mc squared minus mc squared, which is easy. A simple algebra that everybody can understand that. So whenever you're asked to calculate kinetic energy, you have to use that formula. Please don't go into 1/2 mass times velocity squared. I've seen some students do that. That's why I had to go up and say, this is wrong. Read the problem carefully. If you're asked to calculate kinetic energy, what do? Use the formula. Gamma minus 1 mc squared. Do you know how to find gamma? 1 divided by square root 1 minus v squared by c squared. Find that first, and based on what its mass is, do that. Okay, so this is surely, is this a changing term or a constant? What do you think? Okay, what's gamma? Are all the terms in gamma constants? Which one is a variable? The velocity is a variable, isn't it? Oh, haven't we been saying that as the velocity increases, gamma increases? Come on now. And the smallest number it can take is 1. Didn't we say that? So gamma is a changing quantity. Is it an increasing quantity or decreasing? It's an increasing because the smallest value of gamma is. So that's why that's an increase. So I said that increases with speed, and that's the constant. That's called the rest energy. There you go. 2 terms. Very important to understand it. So as the speed picks up, it's this quantity that increases, but this is always constant. Okay, so if the speed is 0, if the speed of something is 0, what's its K? Oh my, I'll hit my head somewhere and die. I don't want to live anymore. Come on. Look at this equation. Look at this equation and tell me, if the speed of something is 0, what's the K? Oh my goodness, thank you so much for making me want to die again and again. Wait, let me try that again. If the velocity is 0, what happens to gamma? 1. So this becomes mc squared minus? Then what is its kinetic energy? Good. Good. No, some people were not saying 0. Not everybody was. Wait, hold on to that thought, because there's going to be a problem. But what happens as the velocity increases? Gamma increases, so what happens to K? So we're talking about kinetic energy all this time. When an object is at rest, its kinetic energy is 0, right? Even by relativistic formulas, that's true. Did you notice that? That is true. Its kinetic energy is 0. But last question, is its total energy 0? Okay, which in these terms is the total energy term? Logic, common sense, which is the total energy term? This is kinetic energy. Come on, I don't want to say anything. Which one? This one? No, that's rest energy. So this is the total energy. Let me rearrange and show you, and then you will understand. Okay, I said this. If V is 0, then kinetic energy is 0, and I make gamma mc squared the subject. That should make it more sensible. Watch. What do you mean by total? According to me, total is the sum of two quantities. That's what I thought. And total energy here means the sum of what? What's that? And what's that? Rest energy. So what would M be? We're not done yet. You can't say mass anymore. You have to say the mass when it is at rest. What? Yes, because with speed, mass also changes. And the formula for changing mass is exactly the same, although I have not written it down. The mass change is given by the same formula. M is m naught, gamma m naught. Same, that's easy. What's m naught? Rest mass. The mass of it, that's unbelievable. Because the concept of mass that we have in our head is like kilograms, how can it change, how does it... And not only that, if something moves with the speed of light, its mass becomes infinite. Okay, wait. Practically it's true. Because when you try to... Have you heard of particle accelerators? What are they used for? For fission, fusion reactions, you need fast-moving particles. Okay? And when you try to accelerate them, and in the beginning it's easy, they'll pick up speed fast. But as their speed increases, no matter what scientists do, they see that beyond a certain limit, its speed will not increase. Do you know why? Because its effective mass is increasing. Just imagine this. There's a person standing here who is lean and skinny, and imagine that I'm trying to push him, and as I push him, he puts on weight. Wouldn't it become harder and harder for me to push him? And then just imagine that it keeps on happening. Just imagine. Isn't there going to be a stage where I can't push him anymore? That's exactly what happens in a particle accelerator. So although this looks like a dream, it's experimentally proven. Now that's one of the reasons why no object can move with the speed of light. I put everything together. I hope you can see that. The mass keeps increasing. It's more and more difficult to increase its speed. And when you come very close to the speed of light, it's like, it's not going to move. You can have a high magnetic field, a very powerful electric field. No. Its speed is not going to change. That's been experimentally proven so many times. So that's the total energy. That's E is gamma mc squared. I'm just writing that again. Gamma is that, you know. And at rest, E is equal to mc squared. Well, actually, it should be m naught c squared. That's where we get that idea from. Do you see that? When something is at rest, it's m naught c squared. So that's the idea that Einstein produced. Has this been proven? Oh, as soon as Einstein gave this, you know, scientists started doing experiments, trying to disprove him maybe. And two German scientists, Otto Hahn and Strassmann, I can't remember the year, 1936, for the first time in history, this is what they did. They took a uranium nucleus, you know how big that is, right? A uranium nucleus, and smashed it with a neutron. The nucleus split into 3 parts. They got barium and krypton plus 3 neutrons. This is called nuclear fission. Many of you have heard about it, right? And what they did, the first thing they did is this. They took the mass of the reactants. This is called a nuclear reaction. They took the mass of barium plus the mass of krypton plus the mass of the 3 neutrons, added that. Are you with me? Then they took the mass of, what are the reactants? Those are the products. What are the reactants? The uranium nucleus and the neutron. They took the mass of that. You know what they found? They found that the total mass of the products is slightly smaller than the total mass of the reactants. They took that change in mass and plugged it into the equation E is equal to mc squared, and they got 220 million electron volts. You know electron volt is a unit for energy, don't you? Which is what they calculated from there. And then from that energy, they went back to the mass. It was exactly agreeing with Einstein's formula. Hey, did anybody understand what I said? The missing mass was exactly the mass that you would get when you divide 220 million electron volts in proper units by c squared. So the world took notice. They said, yes, mass is gone. Mass has been destroyed. And energy has been produced, nuclear fission. And then Otto Hahn, he fell for the green dollar bills. America asked him, hey, come here. Come here. Can you build an atom bomb for us? He said, yes. Strassmann said, no. I don't know who's good or bad, but that's not our issue. Otto Hahn came here and in Chicago, along with Enrico Fermi, 1938, I think, the Italian by birth, they built the first nuclear reactor. Have you heard of a nuclear reactor? The amazing thing is that in one fission you get 3 neutrons. If you heard me. You could use those 3 neutrons to produce 3 more fissions, isn't it? If you had 3 other nuclei lined up. And then you would get 27. 9. And then 9 becomes 27. This is called a chain reaction. Haven't you heard about it? You have. If you control the chain reaction, how do you control the chain reaction? You have materials like cadmium, which can absorb neutrons. And in the Chicago nuclear reactor, they were actually manually pushing the cadmium rods into the reactor. He had people stand there and push because these cadmium rods can absorb neutrons. You got the idea? Because if you do not control the amount of neutrons, what's going to happen? It's going to rapidly multiply. So what they did is they would trigger it and then they would push it in together, so many rods, so it gets absorbed. When they see that the reaction is slowing down, they will pull it out. That's a controlled nuclear reaction. Do you know why electricity is cheap here? As compared to third world countries, it's because most of our energy comes from nuclear reactors. That's why you can have the AC running for 24 hours. But Otto Hahn, after that, he went and said, well, why can't we make it uncontrolled? If you uncontrol it, if you don't control it rather, you will have the atom bomb. All the energy together. And they didn't believe it. They didn't believe it. That's why when they got the opportunity during the World War, they dropped it on Hiroshima. We dropped it on Hiroshima and Nagasaki. We'll never make that mistake again. I'm not trying to apologize or anything because nobody believed it. But history says that the pilot who dropped it, at least one of them committed suicide. On seeing the massive destruction that took place underneath him. There was a crater, I can't remember how deep it was. It killed so many thousands in that instant. And if that was all, then it was okay at least. But the radioactive radiations, the gamma rays, lingered, continued, and it went in and had genetic mutations, and their children and their children's children and their children, till this day, are having differences in their bodies compared to ours. One of the terrible things is a fungal growth that comes up on your body. Just imagine fungus growing on your whole body. You scrape it off, comes back again because of genetic mutation. That is why today we've taken the lead role to say that nobody should ever use this one more time. That's the reason. If it gets into the hands of the wrong people, you know what's going to happen. Because the entire world, the next world war, will be the last one for sure. Should I put all this on?